So we have yet to answer that first motivating problem for the fundamental theorem of calculus, but we've answered the second one, namely that the derivative of the area accumulation function is the original function f of x. So we still want to answer that first motivating problem, that is, how do we efficiently calculate areas under curves? And so let's see, now that we know a of x is an antiderivative, we can say some things. So let big f of x be an antiderivative for f of x. And we know a of x is also an antiderivative for f of x. And do you remember this result that any two antiderivatives differ by a constant for the same function? So I'll say a of x and f of x differ by a constant. So what this means is that, let me write f of x, big F of x. Big F of x is equal to a of x plus some constant c. Now all I'm going to do here is evaluate now my big F of x function from a to b. So let a and b be to x values. Then f of b minus f of a, I can use this formulation to find that. That's going to be a of b plus c minus a of little a plus c. So what's neat here is that the c's cancel out, and I just end up with a of b minus a of a. So what is a of b minus a of a? Well, this is the area under the curve of f between a and b, right? When we saw this with when a of x and a of x plus h, this difference right here was really, this is none other than the definite integral from x to x plus h of f of t dt. And that's true in general, that the difference in the area accumulation function is the definite integral between those 2 points. So this is the definite integral from a to b of f of t dt. So summarizing now, again, we're trying to find an efficient way to calculate this, and we see that if big F is any antiderivative for little f, then this definite integral is the difference between the antiderivative between those 2 points. So that is, in conclusion, integral from a to b of f of t dt is exactly f of b minus f of a, where big F is any antiderivative for little f. And that's part 2 of the fundamental theorem of calculus. And that is how it's proved. All right, so this is pretty neat. Let's actually now practice this. Let's compute some definite integrals using this method, and you'll see exactly how neat it is. All right, see you there.